of EM theory and transmission line. So in the previous lecture, we have discussed about the secondary constants of a transmission line. So we have defined what is characteristic impedance and what is propagation constant, and we derived the expressions for Z0 and gamma, and also we have derived the expressions for attenuation constant alpha and phase constant beta. So in this lecture, we will be discussing about the various impedances that occur or that we get in a transmission line. So first of all, let us derive the expression for impedance at any point on the transmission line. So impedance at a point on the transmission line. So the next topic is impedance at a point, at any given point on a transmission line. Yeah. So for this, let me consider a transmission line. So connected between the source and load. So already we have been into this. Okay. Yeah. So let us we have already derived the expressions for voltage, right, at the point V of x and I of x. So I write the expressions again. V of x is equal to V plus into e power minus gamma x plus V minus into e power gamma x. Similarly, I of x is equal to I plus into e power minus gamma x plus I minus into e power gamma x. Okay. So these are the voltages and currents at any point x. Okay. But this x generally is measured from the load end. Okay. From the source end. Sorry. So from the source end. Now, if generally, right, whenever we are doing practical calculations, so it is also required for us to calculate the impedances or voltages from the load end, because that is the most widely used. Okay. So if we assume that this point, whatever the where we are calculating the voltage and current, let us say that it is at a distance of small l from the load. Okay. So the same expressions we can write in terms of this distance small n. Okay. But only the point is, so x is from source to load. So load L will be from, let's say, or the small l will be from load to source. So the direction of them will be opposite. Okay. So we can replace x as minus L. Okay. Let us replace that x as minus L in the above equations. So the voltage from the load end, right, looking at the from the load end, right, so V of L is equal to V plus into e power gamma L plus V minus into e power minus gamma L, right, and similarly I of L is equal to, right, I plus into e power gamma L plus V minus into e power minus gamma L. So again I am repeating, x is the distance to the point from source end. Okay. So that we have written, looking from the source end, the voltage and current at the point x is like this. Now, if I look it from the load end, right, the point, let us say that it is located at a distance of small l from the load. So in that case, what is the scenario? The scenario is I get like this, because x is, right, opposite to that of l. So we write x is equal to minus l. So I get something like this. Okay. Yeah. Now, right now, we get something like this. Okay. Yeah. Let us take the let us use the expression that we used previously. So in the previous derivation of the characteristic impedance, we have taken, right, V plus, or we got the expression for V plus by I plus as Z naught, right, and V minus by I minus as minus Z naught, right. I think so. In the last video we discussed this. Okay. V plus by I plus is equal to Z naught, and V minus by I minus is equal to minus Z naught. So from this, I plus is equal to V plus by Z naught. Okay. And I minus is equal to, right, V minus by Z naught. So let me use this two quantities in the two expressions. Okay. So in these two expressions, I'm going to use these two terms. Okay. Yeah. So therefore, I of L is equal to I plus can be replaced as V plus by Z naught, okay, into e power gamma L, and I minus, sorry, this is I minus, sorry, yeah. So I minus is equal to V minus by Z naught into e power minus gamma L. So I'm replacing, right, I plus as V plus by Z naught and I minus by yeah, minus, right? There is a minus sign here. So, okay, so minus V minus by Z naught. Okay, right now, now let us right take the ratio of voltage to current. So V of L by I of L, that is nothing but the impedance Z of L. Okay, impedance is the ratio of voltage to current. So voltage to current ratio. So I get Z of L is equal to, so V of L is V plus into e power gamma L plus V minus into e power minus gamma L divided by I of L. I of L is V plus by Z naught into e power gamma L minus V minus by Z naught into e power minus gamma L. Okay, so this is what we get, right? Yeah, clear with this? Yeah, so till this point. Okay, right now, yeah, now let me go on. So this is equal to, right? This is equal to Z of L is equal to, right? So here in both the terms, I will take V plus into e power gamma L as common. Okay. So we can stop here. This is the impedance thing, but I'm just going to fine tune it a little bit. So let us take V plus into e power gamma L as common. Okay. So this will be 1 plus V minus by e power minus gamma L by V plus into e power gamma L. Okay. So that, and in the denominator also V plus into e power gamma L by Z naught I'll take common. So 1 minus, here I get minus 1 minus V minus into e power minus gamma L by V plus into e power gamma L. Okay. So this is what I'm going to get, right? So this and this gets cancelled. So this will be equal to Z of L is equal to Z naught into 1 plus, and the numerator I have V minus by e power gamma L into V plus into e power gamma L divided by 1 minus V minus into e power minus gamma L by V plus into e power gamma L. Okay, so this is one expression for Z of L. Okay, so Z of L is equal to Z naught into 1 plus V minus into e power minus gamma L by V plus into e power gamma L, and similarly, okay, by 1 minus V minus into e power minus gamma L by V plus into e power gamma L. Okay, so we right, using this right, if I know V minus and V plus, V minus and V plus, okay, and if for a given length from the load, right, we can calculate the impedance. Okay, impedance of the point, okay, or at that point. Okay, so impedance at this point, right? But here, if you observe the ratio, the ratio that we got, so this ratio V minus into e power minus gamma L by V plus into e power gamma L. So if you look at this ratio, what is this ratio? Basically, this is, right, okay, if I write like this, V of X is equal to V plus into e power gamma L plus V minus into e power minus gamma L. This is the general expression for voltage, right? So from this, we can observe clearly that this is nothing but the forward component and this is the reverse component. We discussed this, right? So this represents a forward wave, right? And this represents a reverse wave, okay? So here, right? Yeah. So this basically P minus by this is a reverse component. Okay. So therefore, what we can observe is, so this ratio is the ratio of the forward reverse component to the forward component of the wave. Okay. So reverse component to the forward component. So we take this ratio or we represent this ratio by a very important term or very important parameter called as the reflection coefficient of the transmission line. Generally, you represent it as K of L or rho of L. Okay. So this, right, this quantity is the ratio of reverse traveling wave to the forward traveling wave. Okay. So it's a complex quantity. It's not that it's just not a ratio. It is a complex quantity, right? So this complex quantity, right, represents, right, the reverse component to the forward component. Okay, so this ratio, right, basically we call it as, right, reflection coefficient of the transmission line. Okay, rho of L, right, and this rho of L, as I told you, it is a complex quantity. It has certain magnitude, right? Okay, and phase angle, right? There is a phase angle associated with it. There is a right, there is an angle associated with it. There is a magnitude associated with it. Okay, So generally we write it as modulus of K and an angle theta. Okay. So okay. So this is the reflection coefficient. Okay. So let us, if you use that term here, so Z of L is equal to Z naught into, right, 1 plus rho of L divided by 1 minus rho of L. So we can express this, right, like this. Okay. So this is the in general the most widely used formula for calculating the impedance. So given if the characteristic impedance and reflection coefficient, right, are known. Okay. So we defined a new term called as reflection coefficient here. So reflection coefficient will be, right, rho of L is equal to, right, the ratio of this. Okay. Yeah. So this is the expression for impedance at any point. Okay. Yeah. From this, let us use this. Okay. Let us use this expression and let us calculate some special impedances. Okay. Or impedance at special places. Okay. So the expression that I got, Z of L is equal to Z naught into 1 minus 1 plus V minus into e power minus gamma L by e power gamma L by minus gamma L by V plus into e power gamma L divided by 1 minus V minus into e power minus gamma L by V plus into e power gamma L. Okay, so use this expression. Let us use this expression and let us find out the impedances at some special cases, okay, or special places. Okay, yeah. So the first one is load impedance. Okay, load impedance. Okay, yeah. So load impedance means the impedance at the load point, which we generally use represent as ZL. So load impedance means, so here the length, right? So generally what is L? Small l is the length of the point, okay, length to the point from the load, right? So here we are calculating the impedance at the load point itself. So therefore, this is nothing but L is equal to 0. So whenever L is equal to 0, we get the load impedance. Okay. So ZL, which is nothing but Z of 0, right, is equal to, okay, yeah. So Z of 0, let us substitute L is equal to 0 in the expression. 1 plus V minus by V plus into e power 0 into e power 0 divided by 1 plus V minus by V plus into e power 0 e power 0. Okay, so this is when we substitute L is equal to 0. Okay, so this implies Z naught into 1 plus V minus by V plus as 1 plus 1 minus V minus by V plus. Okay, so this is equal to, right, we get Z naught into V plus V minus divided by V plus minus V minus. Okay, so this is ZL. Okay, ZL is equal to, right, Z naught into, right, 1 plus V plus into V minus by V plus minus V minus. Okay, clear with this? Yeah, so this is the term for load impedance in terms of Z naught and this. Okay, yeah. So the same expression we can also express it in a different way. Yeah, if you look at this term, right? So what is this term? V minus by V plus. Okay, V minus by V plus. This is nothing but, right? Okay, so generally, yeah, look at this. Rho of L. What is rho of L? Rho of L is equal to V minus into e power minus gamma L by V plus into e power gamma L. Okay, so if I put L is equal to 0, then rho of 0 is nothing but V minus by V plus. Okay, so the term that I'm talking, V minus by V plus, is nothing but rho of N. Okay, yeah. So let us use that. Let us use that. I think you have understood this, right? So this ratio is nothing but the reflection coefficient. So rho of L is equal to V minus into e power minus gamma L by V plus into e power gamma L. Okay. Now when I substitute L is equal to 0, so rho of 0 is equal to V minus by V plus. Okay. Yeah. Let us use that expression here. Okay, yeah. So ZL is equal to right, ZL is equal to what I get, Z naught into 1 plus rho of 0 divided by 1 minus rho of 0. This is also a very important, right, result that we get. Okay, yeah. From this, right, so I need if I want to calculate rho of 0, okay, rho of 0, so what I will get, so sending Z naught, right, sending to this side, ZL into 1 minus rho of 0. Okay, yeah. So if I solve all this, right, we'll send rho of 0 to this side and take the common. So we will get rho of 0 is equal to ZL minus Z naught by ZL plus Z naught. This is another important relation that we have to impedance. Okay. So the reflection coefficient at the load. This is L equal to 0 means reflection coefficient at the load. Okay. So reflection coefficient at the load is equal to load impedance minus characteristic impedance by load impedance plus characteristic impedance. Okay. And one very important point we can observe here is if ZL is equal to Z naught, if ZL is equal to Z naught, that is if the load impedance is equal to the characteristic impedance, right, then obviously rho of 0 will be 0. Okay, rho of L or rho of 0 will be 0. Okay, so therefore we can say that there will be no reflections coming out from the load end. Okay, or the reverse component will always be 0. There will be no reflections in the transmission line whenever you match the load impedance with the characteristic impedance. Okay, so if the characteristic impedance and load impedance are matched to each other, then we say that the transmission line has no reflections, the reverse component is 0, there are no standing waves, only forward wave exists. Okay, so this is a very important conclusion we have to remember. Okay, yeah, so I hope you have understood the load impedance. Load impedance is nothing but the impedance at the load point. Okay, yeah, so let us go to the another case, right, where we are going to calculate the source impedance, right? So a source impedance or input impedance, right? Source impedance or input impedance of the transmission line. Okay, yeah. So the general expression we got Z of L is equal to right, Z naught into 1 minus 1 plus V minus into e power minus gamma L by V plus into e power gamma L divided by 1 minus V minus into e power minus gamma L by V plus into e power gamma L. So this is the general expression for impedance at any point. Okay. Now, when I say source impedance or input impedance, that means I am calculating from the load point L, right? So so this is my load point, the small l. If the small l is equal to the length of the transmission line, so then I will reach the source point from the load. If I travel the entire length of the transmission line, so then I will get to the source point, correct? So therefore, I will write this as L is equal to capital L, small l is equal to capital L. So therefore, so the input impedance Zin is equal to Z of capital L, which is equal to Z naught into 1 plus V minus into e power minus gamma capital L divided by V plus into e power gamma capital L, right? So again 1 minus V minus into e power minus gamma capital L by V plus into e power gamma capital L. Okay, so instead of small l we have to write capital L. Okay, yeah. So this is the input impedance or the impedance Z of L. Z of L represents the small l is equal to capital L. Okay. Yeah. So this is the second. Right. Now the last one, the very important one, normalized impedance. Okay, at any point. Right. So we have got the Z of L at any point. Z of L is equal to Z naught into 1 minus. I keep repeating this. Writing this thing V minus into e power gamma L, and this will be like this. So 1 minus V minus into e power minus gamma L by V plus into e power gamma L. So this is the impedance at any point. Okay, right. Now what is mean by normalized impedance? Right. So normalized impedance means the impedance that is normalized with respect to characteristic impedance. Okay, so impedance at any point, normalized with respect to characteristic impedance is called as the normalized impedance. So therefore, so here the normalized impedance Z of L bar is equal to Z of L divided by Z naught. Okay, so Zn, the Z normalized or Z of L bar we generally represent. So Z of L bar is equal to Z of L by Z naught. Okay, so this is the normalized impedance. All right. So this is equal to if I take out Z naught common, Z naught gets divided there. So I'll get 1 plus V minus into e power minus gamma L divided by V plus into e power gamma L by 1 minus V minus into e power minus gamma L by V plus into e power gamma L. Okay, yeah, I'll get something like this. So from this, okay, from this, right, I can write this as 1 plus v minus by v plus into e power minus gamma l by e power gamma l, which is again e power minus gamma l. So we can write this as e power minus 2 gamma l. Okay, right? Understood? Similarly, 1 plus 1 minus v minus by v plus into e power minus 2 gamma l. Okay, so all right, I have written like this. Okay, yeah. So from this again, yeah, so Zn is equal to Z normalized is equal to, right, what is V minus by V plus, right? Just now we discussed V minus by V plus is nothing but rho of 0. Okay, yeah, so let us write that 1 plus rho of 0 into e power minus 2 gamma l divided by 1 minus rho of 0 into e power minus 2 gamma l. Clear with this? Yeah, so V minus by V plus is nothing but rho of 0. Okay, so we have written like this. Now from this, again, this is equal to 1 plus rho of 0 can be written as ZL minus Z naught by ZL plus Z naught into e power minus 2 gamma L. Okay, and this is nothing but again the same thing, ZL minus Z naught by ZL plus Z naught into e power minus 2 gamma L. Okay, correct? Yeah. So I have written v plus by v minus by v plus as rho of 0, right? Rho of 0, just now we seen rho of 0 is equal to ZL minus Z naught by ZL plus Z naught. So from that I get something like this. Okay, yeah, so I think you are following this. Okay, yeah, so now this is equal to, right, the Z normalized, Zn is equal to, right, 1, so I'll take ZL plus Z naught as LCM here and here. So this will become ZL plus Z naught, right, plus ZL plus ZL minus Z naught into e power minus 2 gamma L. Okay, right, that's what happens. And here ZL plus Z naught, right, ZL plus Z naught minus, okay, ZL minus Z naught into e power minus 2 gamma L. Okay, yeah, this is what we are going to get. So from this, right, from this, so in the numerator, right, if I take the ZL terms common, ZL terms common, so 1 plus e power minus 2 gamma L, right, and Z naught terms common, 1 minus e power minus 2 gamma L. Okay, right, in the numerator, what I am doing, I am taking the ZL terms common, ZL, right, here it is 1, here it is e power minus 2 gamma L, right, and similarly Z naught terms common, 1 minus e power minus 2 gamma L. Okay, right, and this, okay, in the denominator we get ZL, if I take ZL as common, 1 minus e power minus 2 gamma L. Okay, and this will be Z naught into 1 plus e power minus 2 gamma. Okay, you hope you have understood, right? Okay, now this 1 plus e power 2 gamma L, e power 2 gamma L is nothing but e power gamma L divided by, okay, e power minus gamma L, we can write like this, e power minus gamma L by e power gamma L. Okay, so if I take the LCM out of that, all these terms, okay, so what I will get is, right, like this, this is equal to ZL is equal to e power gamma L plus e power minus gamma L plus Z naught into e power gamma L minus e power minus gamma L divided by, okay, ZL into e power gamma L minus e power minus gamma L plus Z naught into e power gamma L plus e power minus gamma L. Understood? So again, e power minus 2 gamma L, right? E power minus 2 gamma L is nothing but e power minus gamma L by e power gamma L. So if I write like that and if I do the LCM, all the things we will get the same. Okay, right? So from this, right? From this, Zn is equal to the normalized component of Zn is equal to, right, what I get, ZL into, so this is nothing but e power gamma L plus e power minus gamma L is nothing but cos h gamma L, right, and this is nothing but sin h gamma L. Okay, so by 2 will be there, that we can cancel out from all the terms. Okay, again this will be ZL into sin h gamma L, right, plus Z naught into cos h gamma L. So very important derivation for us, right? So we got the Z normalized as ZL into cos h gamma L plus Z naught into sin h gamma L, right? And ZL is ZL into sin h gamma L plus Z naught into cos h gamma L. So this is the expression for normalized impedance of a transmission line. So normalized impedance means Z of L by Z naught. Okay, Z of L bar is nothing but, or Zn is nothing but Z of L by Z naught. So Z of L we know, right? We have divided it with the Z naught, and just we made some mathematical manipulations. So we have used the result, we use rho of 0. Rho of 0 is equal to, right, we write it as V plus by V minus. Okay, V minus by V plus. We used that. Okay, and rho of 0 we can write it as Z naught minus ZL minus Z naught by ZL plus Z naught. We have used that condition, and from there on I just used the simple mathematics to get this equation. Okay, so this is of importance for us, not now, but we will understand where it is important later. Okay, so these are the various impedances that are available in the transmission line. Okay, so first we have calculated the impedance at any point, okay, from the source end. Okay, then from there we defined what is load impedance, what is source impedance, and then we have derived the expression for normalized impedance from the load end. Okay, so all these are the various cases. We got one very important factor called as reflection coefficient, right? So what is reflection coefficient we derived, and when we can get this reflection coefficient to be 0, we also got the condition. Okay, yeah, so hope you have understood these various impedances that are available in the transmission lines. In the next video we'll be taking this further, and we will understand the concepts of lossless transmission and distortionless transmission. Right. Thank you.